I find it so intriguing, actually, to think how ancient technology is key for modern technology in a sense. If you think about it, this is some of the most cutting edge to me. I
Mm.
mean, modern particle physics is as cutting edge as you're going to get, and yet it requires for certain tests at least archaeological materials. I find that absolutely fascinating, ancient tech.
What's up, you scholars of enlightenment? Dr. Sam Gregson, particle physicist, here again. I hope you've had a brilliant week and have a fantastic weekend in store. Now, today, we're going to be discussing the fascinating history and recovery of low background metals. Now, you may not realize it, but particle physics and archaeology actually have significant crossovers. Radioactivity is harnessed in numerous dating techniques. Muons have discovered inaccessible voids in the Great Pyramid of Giza, and low background metals salvaged from sunken Roman triremes are even being used to search for dark matter and allegedly in spacecraft going beyond our solar system. Today, we will discuss the nature, use, and recovery of low background metals from historic sites and ask whether it's appropriate to plunder the past to potentially illuminate the future. To help me do that, I'm joined by a phenomenal special guest, archaeologist Dr. Flint Dibble. Dr. Dibble is a Marie Curie Research Fellow at the University of Cardiff, where his research focuses on ancient Greece, including such topics as urbanism, climate change, religious ritual, and everyday life. Dr. Dibble has a brilliant YouTube channel where he makes archaeology fun and accessible without resorting to sensationalism and clickbait. He's also staunchly against the practice of pseudo-archaeology, where the feats of ancient people are attributed to aliens or long-lost cultures without appropriate archaeological evidence. He even plans to challenge Graham Hancock and his ancient apocalypse hypothesis on the Joe Rogan podcast. So I couldn't ask for a better guest to help me dig into the controversial treasure hoard that is low background metals. So Flint, I've been wanting to talk to you for a while. So today we have the what do they say, the greatest crossover since Avengers Infinity War between particle physics and archaeology. And we're going to be discussing particularly low background metals. So do you want to kick us off?
Yeah, for sure. Yeah, I'm glad that you invited me on. And yeah, we've been talking about this and we sort of popped upon this as a way to cross over physics and archaeology with something fun and new.
Exactly.
And so, yeah, we've discovered, at least to me, this new idea of low background metals that people are using archaeological artifacts to contribute to scientific experiments. So what are these and why are people using archaeological materials for modern science?
Yeah, that's a very good place to start. We'll actually define what we're what the hell we're talking about. So these low background metals, these are metals that have very low levels of radioactivity within them, essentially very small amounts of radionucleotides that are decaying, so they're giving out very low amounts of particles. So all kind of metals and rocks tend to have a low level of radioactivity, but these low background, as the name suggests, metals have much lower levels of this radioactivity. Now, why is this important? Well, because
I'd like some for my house, maybe. I don't.
So good point to make straight away is that these levels are not particularly damaging. They're not particularly dangerous. They're we are exposed to a low level of background radiation all the time. Yeah, and these low background radiation metals, they even have background levels below those usual background levels that normal stones and metals have. So why do people covet these? Why do people care so much about them? Well, imagine that you're creating a very precise tool to detect radiation, a Geiger counter, for example, the little click, 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 click that we see in, Chernobyl documentaries and things like this. It's no good trying to detect external radiation and particles coming in if the device that you've made your Geiger counter out is emitting those particles itself, because it's going to detect those and interfere with the signal. So you want to set a good baseline in your accurate scanning device. So these low background metals with these low levels of interference in that sense are very important for sensitive particle physics experiments, for medical equipment where you want to get precise measurements of radioactivity. So if you want to capture very rare interactions of particles, or you want to measure the interactions very, very precisely in terms of numbers, it's very important to minimize that interference from your materials in your device. And that's why these low background metals are so sought after.
All right, but that's like a lot of physics.
That is a lot of physics, yeah.
Where's the archaeology come in? Why do you need old metals? Like, why do they need to be old?
That's a very good question. So I guess the question is, two metals that particularly come up are steel and lead. So let's start with lead, because this is maybe the one that's a little bit more archaeological, going back a bit further in time. So newly made steel and newly made lead are both a little bit radioactive, but for two slightly different reasons. So let's start with the lead. So lead that occurs naturally, that we just dig out of the ground, tends to be mixed up with radionuclides that are in the soil. So things like uranium-235, this is knocking around in the soil. And when we dig it out, you have an amount of uranium-235 in there. Now, that uranium-235 decays to lead-210, which is also radioactive. So once you dig it out of the ground, you have this amount of lead-210 in the sample. But then the people that refine the lead, they get rid of all the uranium, they get rid of all the other radionuclides, and the only thing you're left with is this radioactive lead-210 isotope, which is a small amount of the lead that you've dug out. Now, over time, that radiation will decay away, and you'll just be left with inert lead. But this takes quite a long time. I think the half-life for lead-210 is about 20 years, or just over 20 years. So it takes a long time. So if you can get lead that was processed and had all these impurities removed back in the Roman era, for example, or in the Greek era, you can have very, very low background lead today. Whereas any lead that we dig out of the ground now, you're essentially starting the clock on that lead-210 now. It hasn't had those thousands of years to become inert. So people are really, really interested, as you've probably seen in your field, of getting hold of lead that was refined by the Romans or the Greeks or other ancient civilizations. So that's the reasoning with lead.
You know, I actually did not know that. But what's interesting to me is how similar this process is to how radiocarbon dating works, right? So in a sense, radiocarbon dating works with calculating that time, that half-life of radioactive carbon decaying. And you know, so in a sense, an organism, whether it's you, me, a tree, or a goat, is living in ancient Athens behind me, and it's absorbing radioactive carbon from the atmosphere.
That's right.
And then it takes time to decay, and that's what we're testing. We're testing that ratio of decayed carbon. But, you know, there's a problem that occurs. And so when we developed these methods in the 1950s, it was in 40s, it was just at that time that nuclear testing was going on.
Yeah.
And so we can't do radiocarbon testing from modern times because the atmospheric radioactive carbon has been screwed with so much, you know,
by us physicists. If you've been watching Oppenheimer in the cinemas recently, yeah.
But that, of course, you know, that has not impacted, which is good for us. It's not impacted the proportions of radioactive carbon in ancient organism remains, you know, bones and teeth and seeds and wood, and so we can still do the tests, fortunately, on things before 1950, and it's because of that nuclear testing, you know, that we call 1950 the present. So we take before present.
So we're all a lot younger than people will say. We're all we're all just coming up.
We are all 74 years into the future. You know, like right now is the future. Yeah. But yeah, okay. So that's cool. Lead makes a lot of sense. What about steel then?
Yeah, so steel. So that was actually a really nice segue that you did there. So essentially in 1945 with the Trinity test. So I think I've got a nice couple of images here. So with the Trinity test, the first nuclear test above ground, this was July 19th, 1945, set off this big bomb in New Mexico. If you watched Oppenheimer. You've got the idea. Exactly right. So this
is Oppenheimer meets archaeology, man.
Exactly. These are the crossovers we're going for today. So this was the first successful atomic bomb detonation, and they've been a lot since, right? So this is the start of this issue, but it's not the end, because there were, over the period up to about 1963, so over the next kind of 20 years, there were hundreds to maybe 1,000 of these nuclear tests, maybe slightly more. I've got to check the exact numbers, but there were, I think it said 528 above ground tests since 1945. So lots and lots of these tests. And what did that do? Well, it did exactly what you said. It kicked up a load of radioactive particles, radioactive dust, radioactive nucleotides into the air. So the atmosphere became a little bit more radioactive. Your plutonium-239, strontium-90, cesium-137, technetium-99, all these radionucleotides got thrown up into the air. And what this did was it increased the amount of.
By the way,
please.
all those particles sound like they're Latin, but they're not. The ancient Romans did not discover cesium.
Yes, we probably stolen some. Yeah, we like to steal a lot of conventions.
A lot of scientific terminology uses Latin and Greek, and one of the good things about that is it makes this sort of scientific terminology universal around the world. So it's a language that makes sense, if you see what I mean.
And we always start with like ABC, but then we run out very quickly. So we start putting mu's and deltas and all sorts of stuff. So yes, so this increased the amount of radioactivity that was in the environment. Now, why is this useful, or why is this important when we're talking about the production of steel? Well, steel, or a lot of steel, up until recently, used to be made by a very simple process, which was called, when I can bring it up, the Bessemer process. So in this Bessemer process, essentially air or oxygen from the environment is just fired at pig iron to try and oxidize the impurities that are in it, and clean it up, basically, make it more suitable for being used in various processes. Now, why is that a problem? Well, because that air, that oxygen that's been knocking around in the atmosphere has taken up some of these radionucleotides. So if you fire it into your pig iron, the steel that you create contains some of these radionucleotides, and then those are going to decay later, and that steel is going to have a slightly higher level of background radiation. So if you want to use this in a very sensitive process, if you want to use this in a Geiger counter, if you want to use this in a particle physics experiment, you've now got particles being given out by the walls of your piece of kit. And that's something you can't necessarily, at least until recently, deal with. So it's a slightly different reason than the lead, but the same kind of problem, that you have this higher level of radionucleotides in the metal. There's a couple of really interesting things that go with this, actually. He talks about radiocarbon dating. They've also been able to, based on these levels of radiation in the atmosphere, if I can find it. Maybe I didn't bring it up. Yes, I did bring it up. They've actually been able to solve wine fraud mysteries as well. So you have
makes sense.
You have these higher levels of radiation in the atmosphere, and your grapevines are taking up these higher levels of radionucleotides in the soil and in the water and in the carbon dioxide and in the air that they take in. So the grapes that go into making some counterfeit wines, people will say, this is a vintage that was taken from, Louis the whatever's cellar. And then when they do the test, they find that they have these higher levels of background radiation, which suggests they actually were bottled after 1945, or at least the grapes were culled after 1945. So you can do a hell of a lot with these cutoffs. You can actually see this signal in wine, in organisms, in steel. You can see you can see it in a lot of places, in the radiocarbon dating, as you correctly said. So
this is also why, by the way, geologists think that this is the cutoff for the start of the Anthropocene, because it's a signal that you can see worldwide, and future, whether it's future humans or future other people, other organisms, they can always detect this start across the world. It's a great example of how humans have just modified the entire world.
Not necessarily in the best of ways, like spraying radiation all over the place. But okay. So this is what low background metals are, and that's why lead and steel are slightly higher in radiation. One of them, because when you dig them out of the ground, you need to strip away some of the things that they're contaminated with, the uranium in terms of the lead, and then with the steel, because you're spraying all of this air into it, which is full of slightly higher levels of radionucleotides. Now, with steel, we'll probably talk more about lead today, because the steel, the actual levels of that radiation, if I bring back the little plot that we had, this is a log scale, so it's actually decreased a lot since 1963. So 1963, they put in place some legislation. The US, the UK, the Soviet Union. These were the major bodies that were undertaking these nuclear tests. They put in place a partial test ban treaty banning above ground nuclear weapons testing. So 1963 was the peak of this problem. So if you were making steel in 1963, it's very, very, it's got kind of 10% higher level than normal, 5 to 10% higher level than normal background level. But over time, obviously, these radionucleotides have decayed away. And now it's about a 30th of that level. So it's still slightly above background, but not so much for steel. But the problem remains for lead because you still haven't dug it out of the ground. So for steel, it's not so much of a problem nowadays because the levels have decreased since 1963. We've also come up with better computational ways of dealing with backgrounds in particle physics detectors and things like this. And also different ways of creating steel. Like there's the reduced oxygen process, which uses kind of purer oxygen, which has already been purified of some of these radionucleotides. So with the steel, which I'm sure we'll talk about a little bit, but this problem's kind of largely gone away. Not perfectly. It's nice to obviously have low background from the start and not have to do any workarounds or use more expensive processes. But mostly for steel, this problem's gone away. But the problem for lead...
It's also going to be a more modern sort of archaeological site because steel was not developed until the 19th century. So when you're dealing with this lead, it's going to be much older. We're talking ancient in a sense. Yeah,
and that brings more of your skills into your wheelhouse. So I think lead is going to be definitely more of the focus of this. So that's why we're interested in low background metals and why steel and lead, two of these materials that are so widely used, were widely used in the ancient world as well, and are now used in particle physics experiments, are so richly sought after.
I find it so intriguing, actually, to think how ancient technology is key for modern technology. In a sense, if you think about it, this is some of the most cutting edge to me. I mean, modern particle physics is as cutting edge as you're going to get, and yet it requires for certain tests at least archaeological materials. I find that absolutely fascinating. Ancient tech.
Well, because we screwed around with the atmosphere, and now we're going back to the ancients to clean it up for us. Basically,
well, not in this case with lead. It's not because we screwed with the atmosphere. True. It's actually because it needs to have been mined, several hundred or thousands of years ago. So what are some of the archaeological examples that have been used in the past to be able to with these sort of low background metals? What do you know about? Because I mean, this is, like I said, this is not actually well known among archaeologists. This is a newer thing that we don't think about. So you tell me what has been used so far.
So let's start with the steel, then the little bit more up to date, and then we'll go into the lead, because I know you have a lot to say about lead, and I didn't realize how pervasive lead was in the ancient world. I'm quite worried about those ancient people and how much lead they were using. So let's start with the steel. So in terms of steel, so nowadays most of this low background steel comes from, and I've got some nice pictures when I can find them. So comes from the hulls of battleships that sunk before 1945, and that makes sense. They were on the bed of the ocean before these nuclear tests were being done. So one of the most famous sources is the German World War I naval fleet that sunk off the coast of Scotland in a kind of shallow, flat stretch of seabed known as Scarpa Flow. So this is a very kind of famous case. So in 1919, basically the First World War came to an end. Well, just before that. But rather than turn their ships over to the British, the Germans thought that it would be better to scuttle them off the coast of Scotland. And of course, these ships sunk to the bottom of the ocean. And some cases where they've been used, or at least been rumoured to have been used, were where these have been basically cut away huge hull plates of these ships and these low background steels, and then used them in hospitals in Scotland for total body counting rooms, which we'll come on to later, I'm sure. And then another example of this low background steel is cutting away plates similarly from the where is it? The Indiana, which is another battleship, a US battleship in this case, and using them in hospitals in Illinois again for these whole body counting rooms. Maybe I'll say a little bit about what those are now. So the idea with those whole body counting rooms, the reason that they were doing this, I think I've got a nice picture if I come on to it. Yes. So these are rooms where people who had been exposed to radiation would go inside, and essentially you would have a Geiger counter that's above them there, and it would measure how much radioactivity was coming off of them. Now, the problem with that is if you go into a normal room, you have a level of background radiation, which is coming from the rocks and the materials that just make up the hospital. The walls of the hospitals are made of rock. There are rocks and metals around in the hospital. You're going to get interference with your signal. Now, if you put someone inside essentially a steel box made of low background steel, that low background steel box can stop those particles from outside coming in. And the only signal that you're going to see is essentially the radiation that's coming off the patient.
So wait a second. Is this why I don't get cell phone reception in hospitals?
So they do a lot of this. So you can imagine when you're in hospitals, I don't think they use these steel plates all the time now, but you'll notice, or someone might have noticed when they go for a scan, the person who does the scan very quickly wanders off behind a shield. And the reason for that is because one dose of radiation is not really going to do you much harm statistically. If you go and have an X-ray or a CT scan or whatever, don't be concerned. But if the person in the hospital working on that is doing 10, 15, 20, 30 every single day, they don't want to be getting flashed with that radiation. So they step behind a shield. You could use something like this, but in that case, you only need the shielding. You don't need the low background. Yeah. So in this case, they wanted these boxes so that low background steel wouldn't interfere with the count that's coming off the person. So there's rumors that this was done with battleship plates salvaged off the ocean in the US and in the UK, in hospitals in Scotland and hospitals in the US, a Utah medical center. So these are a little bit sketchy, but these rooms definitely existed. And the allegations or the suspicions are that they use these low background steel plates. So if you want to find low background steel, a good place is to go looking at these warships that sunk before 1945.
So don't just go looking for it, please.
If you wanted to find on the internet, type in low background steel sunken ships. Don't necessarily go out there yourself with an underwater torch. In terms of the lead, which I guess is going to be much more in your wheelhouse, probably pun intended. So the low background lead tends to come from the cargo holds, and I can bring up some nice pictures here as well when I can find them. So we'll go on a little bit. Comes from the cargo holds of even older ships. So again, we're going back maritime, but as you'll be well aware, the Roman Empire used lead extensively in lead pipes, in baths, in coins. So when these ships sunk to the bottom of the ocean, they were often carrying large amounts of lead ingots, which could be used for various things in the Roman Empire, various manufacturing of various items. Like I said, these have a kind of very long half-life. So nowadays they've become quite inert. So you can find these ingots at the bottom of the sea on these, if we can find these old Roman or Greek shipwrecks, and these are the places where we want to find them and where they've been kind of dredged up from. Flint, I wanted to. So while we come on to lead, can you tell us about any specific shipwrecks that have been discovered, which are, I don't know if gold mines for lead I've put in the question, which sounds wrong now, but yeah.
No, that's definitely the wrong way to put it. Let's not think of anything.
And a bit of alchemy going on there, right?
I just want to make a clear point here. Let's not think of any of this stuff as sort of
like a bounty
stuff to be mined.
Yeah.
That's really the wrong way to think about it, because this is very much a finite resource. Even if you think about that steel only comes from shipwrecks over the course of 100 years. Yeah. So if this is a valuable resource, for use in modern scientific or medical situations,
Yeah.
we could quickly use it up if we just go ahead and
Yes.
mine it very quickly. Because
Yeah.
we have so much more uses for things right now. And lead at the same time, I'll tell you in a bit about how much lead there was in the ancient, Mediterranean world, for example. But at the same time,
there's no more being made.
The amount of
so,
lead
yeah.
that was made then is a lot less than what we make now for our various...
we didn't have huge factories pumping out and things. So a lot then is not necessarily how we might define a lot now, or
and so
not easily replaced.
But yeah, there is one particular shipwreck, the Boofarer shipwreck. The one that's up here. It's actually considered the largest ancient Roman shipwreck. And it was discovered in the early 21st century. And so its lead was used for an Italian particle detector, I guess.
Particle detector, yeah.
Yeah, so what was the name of that detector? The Cuore?
So the Italian word for heart, which I think is cuore. Now, if I butchered that, I apologize, but Cuore, yes, cuore, the Italian name for heart.
And one of the things that's interesting is, so the shipwreck was discovered by local divers, and it was categorized, of course, by underwater archaeologists. But it was actually these particle physicists who helped fund the excavation because they were interested in the lead itself. And so it's actually a really cool ship. I mean, from an archaeological perspective, it's been under excavation since 2006. And we know when it was sunk. It was sunk between 50 and 80 BC, but actually probably closer to specifically like around 66, 68, somewhere around there.
You say since 2006. I'm guessing this takes a lot of time because you're underwater and you're trying to do things responsibly and catalog everything, and everything's more difficult if you're under.
It's a huge job. And I mean, if you're thinking about it, it's clear from doing some reading on this that the lead was clearly raised early on because that was then provided for Cuore, for the Cuore particle accelerator, particle detector. But the excavations continued because it wasn't just a ship. It had lead. It had the lead ingots. It had, how many was it? It was.
I think they've said. I think when you mentioned it to me, you said two. Excuse me. Each ingot weighed 200 pounds. So 200 Roman pounds, 65 kilograms. Now, how many were there?
I think I thought it was something like 1,500.
I think in a couple of thousand.
Yeah, and then they ended up 15% of them were used for this Cuore facility. Here, wait, let me get the number.
No problem.
Only the most damaged ones were actually transferred for that. And it was I remember it being 15%.
So they said here, if you said it was 15%, they said they gave 120 ingots for this particle physics experiment, which we're going to talk about in more detail later. So 120. So if that's going to be your 10-15%, so that'd be 80. So yeah, we're talking about of order of 1,000 ingots or more.
Yeah, and only the really damaged ones were actually given. Which is important because these ingots were pretty interesting. They actually had stamps on them. Many of them had stamps that said Imp Aug Ger Ner Ka, which is abbreviations for Imperator Augustus Germanicus Nero Caesar, right? And so specifically, this is labeling that the emperor, probably Nero at the time, was the one that owned all this lead that had sunk in the shipwreck. And so this is an interesting shipwreck also because we can map out its exact route, right? So it actually took off from around Cadiz, so near southern Spain, and it made several stops along the way, and we know this because of the cargo in the cargo hold. And it was on its way to Italy when it looks like some strong winds blew it out of deep water into shallow water, causing it to be sunk. And so we have this kind of level of detail for the Roman economy at the time of where it's going with what's on it. But its main cargo was not all these lead ingots. It was actually 2,500 jars of salted fish and fish sauce. And so this is a huge part of the Roman economy, particularly the Spanish Roman economy at that time. So we actually have in Rome, there's this mountain called Monte Testaccio. It's an artificial landfill filled with these kind of ceramic jars, and they come from Spain and Africa and elsewhere. And we can sort of put together the entire, import of this kind of stuff, fish sauce and wine, through this artificial landfill of all these import jars. And so the cargo on this ship had 2,500. That landfill, by the way, has it in the millions, of course, right? The one in Rome. And, so this tells us a lot about what's coming in. And I mean, the preservation of the underwater site is just amazing. It's above and beyond what we find on land. The sort of waterlogged conditions mean that we have the wood of the ship itself. And so the excavators have been able to put together reconstructions of the ship. By the way, the excavators are Carlo Dewan and Franca Cibacchini. I hope I'm not mispronouncing their names. And so the preservation is amazing. They can put together the ship and reconstruct it, and they can reconstruct the packaging of this cargo. For example, these amphorae, these ceramic storage jars, they're stacked at the midships, 4 levels high, in a geometric quincunx pattern for stability. And each amphora was cushioned with grapevine shoots as dunnage, right? And so that means they've actually been able to recover these grapevine shoots that they're using to kind of cushion these wine jars. And I mean, this level of preservation, it's just unbelievable. And it's something that you don't usually get above ground. Like you could think about lead. We're talking about the lead here. Lead's not going to preserve if it's exposed to the elements. Or even more importantly, lead will be robbed and melted down and converted into something else. It's reused, right? It's a valuable material to anyone.
So if it's on land and somebody can get hold of it, it's going to be gone. It's not going to be pure Roman lead anymore. It's going to be used for something else.
I mean, that's why we mostly have just sort of doodads that have become trash accidentally, or, in a destruction sort of horizon, a shipwreck like this, or maybe in infrastructure. So like the pipes and stuff like that, because infrastructure is more difficult to rob out, being underneath a building or a ruin. So it's a very kind of unique find, and I want to really emphasize that these kind of underwater archaeological finds, they're oftentimes better preserved. We oftentimes think that destruction is a bad thing, not for an archaeologist. Destruction is a good thing for an archaeologist. We love destruction horizons. We love diseases because they kill a lot of people at once. We love,
in terms of the academic learning that we can have, not necessarily for the people, right? Just to clean that up for people.
We love when things burn down that preserve stuff. We love when ships sink. I mean, yes, it's a tragedy. I'm not going to deny that.
But strong signals that are going to show up in that historical record, so that you can tell what happened.
It provides a unique sort of snapshot, and that's what this kind of shipwreck is a unique kind of snapshot. So it's not even just that sort of Roman lead itself is fragile and finite as a resource. The kind of context we get it from is even more valuable, right? And so it's a very useful context for understanding. I mean, I think I saw that one of the excavators, I mean, this is probably just a stab in the dark, but they were thinking, oh, maybe this lead was for some of the infrastructure and rebuilding that happens in Rome after Nero's fire. And that's a little fantastical, but this still provides, an important snapshot. And, just to make another interesting point about how valuable this kind of evidence can be, these kind of stamps we were talking about on the lead itself. These kind of stamps, the Romans stamped a lot of things with ownership sort of symbols, whether it's these amphora or lead or bricks. And so just recently, archaeologists in Italy have discovered that the Pantheon, all of our historical sources tell us it was the Emperor Hadrian who built the Pantheon. But actually, the brick stamps on the bricks, only restudied in the last 20 years, they tell us that it was started under Trajan. And so this kind of like more mundane evidence, you never know when it's going to come in handy to actually tell us about something big and important. And we need to preserve that for future.
I'm just going to go around writing my name all over stuff, Flint, and burying it.
That's what the Romans did, man. Seriously, that's what the rich and powerful did. They wrote their name on everything. And, I find it funny how we have these debates about taxes today, right? In ancient Rome and Greece, only the rich paid taxes. You and me, we wouldn't be paying taxes. It's only the extremely wealthy that pay all the taxes. But what they get in exchange is they get their name on everything. Right?
I mean, you can buy a sports hall in a school nowadays and get it named after you. I guess it's kind
Yeah,
of the same thing.
exactly. Yeah.
Fair enough.
But yeah, so lead was a really important component of the ancient, Roman.
So this is what I want to come on to now. So
yeah.
So we've got that kind of, we understand where we can get this lead from that we want to use in particle physics detectors. We understand why we want to use it. We're going to talk about the specific cases in a minute. But we said that we can get them from these shipwrecks, and that raises the obvious next question, is that why is this lead and why are these lead ingots so pervasive on Roman ships, Flint? Was lead used incredibly extensively in the ancient world? What was it used for? Because nowadays we think of lead as, an incredibly toxic material. We don't really want too much of it around us. Whenever someone talks about lead, it's to do with fumes or, petrol, or someone's breathed it in and someone has been poisoned. Yeah, or lead paint. That's right. So was it very pervasive in the ancient world?
Yeah, I mean, so I wouldn't say it's pervasive on shipwrecks, because every shipwreck is going to be its own unique cargo. But certainly it was extremely pervasive. There's a lot more lead around in sort of the ancient Mediterranean than there would be today. And there's a reason for that. Silver was one of the most important precious metals, and lead is a byproduct of silver mining.
Right.
So it was available cheaply because there was all this lead on hand. And so what that means is it's used for kind of everything. And so, because they didn't understand it was so toxic, like we do today.
That helps for its use if you don't know. Yeah. If you don't know how horrible it is.
And so we have mines that we've excavated. I've been in some outside of Athens in Lavrio. There's a whole mining industrial landscape there at the site of Thorikos. In fact, it's actually quite amazing. Silver.
I think we can bring up an image of that. I've definitely got it somewhere. Let me bring that up for people to have a look here. So,
this one. Yeah. This is the industrial quarter. If you click on the image itself, I think it'll pop up in bigger. Yeah. Yeah, this entire area is an industrial quarter used for refining silver ore and lead from the mines at Lavrio, which were some of the most important sources of ancient Athens wealth. And so you can just walk around this today and visit it today. It's a fantastic example of an industrial landscape, to scale, and the ways we talk about people modifying the landscape. This entire area, you can see it even from ancient times.
So lead is a byproduct of that. When they're mining the silver, when they're purifying the silver, that lead is being produced, and then let's use this for other things.
They basically say, let's use it, and it's super cheap. So I think I saw you had an image of an extremely large vessel with some lead repairs on it.
Yes.
Popped up for a second. Yeah, this is actually from a conference poster by Gina Tibbett, who I excavated with at Pompeii a long time ago. So this right here in the middle, this is from Pompeii, one of the city blocks there. This large vessel here in the middle of the poster, that's bigger than you and me put together.
I can probably zoom in a little bit if I maybe not. I don't think
that's okay. That vessel is huge. It's bigger than you and me together, right?
Okay.
And so these types of vessels, they'd be used for storing huge amounts of agricultural produce or commercial products or something like that. We're talking in the thousands of liters. And so it could be used for decades or hundreds of years even. And when one of these big vessels cracks, you got to repair it. And so they'd repair it with these kind of lead staples that you see.
Agricultural products and lead staples. Yeah, doesn't sound great for today, but yeah.
I mean, most of it's on the outside, but yeah,
okay.
I mean, look, we also have examples of lead drinking cups. We have examples.
We've had lead pipes for a long time. It's not so long since we got over this. So yeah,
we have all the lead pipes in ancient Rome. We talk about, was that the downfall of Rome? No, it was not the downfall of Rome.
Got the pipes in here, the Roman.
Yeah,
lead pipes,
but at the same time, when they were first installed, or when they were sort of repaired, they would have, contributed lead into the atmosphere that people would have absorbed. And we know that many skeletons had higher incidences of lead in the past, but it's not just due to the pipes. Because, by the way, once enough water runs over them, this mineral accretion gets deposited called sinter, and that stops the water from absorbing any of the lead. It means it's no longer in contact with it. So it wouldn't have caused the downfall of Rome, no. But lead was pervasive and in the atmosphere, and even more so, it was used in people's makeup. So until the Renaissance, people were using lead. Yeah, you have an image there as a component of makeup. If you want to, powder your face to make it lighter and fairer and whiter, you would use lead up until recently. And so, and it was also used in all kinds of medicine. So people were purposefully ingesting lead.
Yeah.
And this is just because they didn't understand that it was toxic. It kills you slowly rather than quickly. And so, people did not recognize this until recently. And lead was used everywhere. Another example that I always find funny, is many of the temples in ancient Greece and Rome, the stones were actually, if you scroll down, were clamped together using lead clamps. So right here you see two stones. One of them is cracked. It's not always for cracked stones. And what's left to us is the hollow where this clamp would have been. And this would have been a lead clamp. It's been since robbed and melted down and reused, all this lead. But we have the indentations for these clamps in, millions of architectural stones from the ancient Mediterranean. And this article is actually kind of interesting because it's talking about the modern repairs to the Parthenon, sort of this thing right behind me, right? And when this was reconstructed and rebuilt into the monument that you see today, about over 100 years ago, they used iron clamps because they used iron at that time in architecture and construction and things like that. And what they didn't realize, of course, is that iron over a long period of time, even though it's in there very tight, the humidity from rain and things like that, it causes it to rust and expand, which causes new cracks to form in these, in these stones from thousands of years ago, these architectural stones. And so now, whenever you go up to the Acropolis, it's under reconstruction. They're trying to re-put in new clamps that won't rust. And the ancients were smart; they knew that lead did not rust, so they were using these lead clamps in architecture throughout the sort of ancient Mediterranean. So it was it was used for everything. It was used for weapons. It was used for, cups and plates and bowls. It was used for utensils and repairs and architecture and cosmetics and medicine. Lead was everywhere.
I think you said it was even so pervasive that they found it in kind of Arctic ice cores, Greenland ice cores. It was so used by the ancient civilizations.
This was a recent study that was published, actually. And so they found that there's traces of lead that show up in different amounts in these Greenland ice cores, and they can track them, of course, with the ice deposition each year. And so during periods of the height of the Roman Empire, when they were mining more silver, you could see a spike in the amount of lead in the Arctic ice cores because it's being released into the atmosphere. And then, of course, when silver mining drops down, there's less lead in these Arctic ice cores. So it's actually a proxy for understanding pre-modern sort of mining. And it goes to show it's not just, we've not been modifying the atmosphere of this world just since nuclear testing. We have been modifying it for a very long time through our activities. I mean, people, we are pretty intrusive on this planet that we live on, and we need to pay attention to that because now we know the dangers of lead and we know the dangers of radiation. And it's like, whoa, what are we doing? Yeah.
Now we go on to carbon dioxide, and we'll deal with that next.
Seriously.
So amazing. So we know where this lead is that we can go and find, and this low background steel. It's a lot of it's on the bottom of the oceans. And we also understand why that's the case, because it was used in battleships, and it was used pervasively in these ancient cultures. I guess that brings us a little bit onto kind of what it's used for today. So we talked a little bit about that, but maybe if we give some concrete examples. So I mentioned a lot of these metals are going to be used in particle physics detectors and experiments, usually where you need high sensitivity. So you're either looking for very rare processes, so you're looking for a small number of processes, or you're looking at something that happens frequently, but you want to measure it very, very accurately. They're basically the same sort of problem. So in terms of the low background lead, one of the places where this got used, and you kind of mentioned it, and we'll come on to Kaware. But before we do that, one of the places that this low background lead was used was in the cryogenic dark matter search, or CDMS experiment, which was in Minnesota, and it aims to detect particles that make up dark matter. So the idea here is that obviously we haven't found dark matter as yet. Dark matter, because we haven't found it, must be something that interacts very weakly with the particles that we're made of, because we're not constantly being bombarded with dark matter as far as we're aware. And if you want to detect these very rare interactions, what you can have is an isolated vessel with a huge shield around it. And that means not a lot of stuff is going to get in. Now, what can get in are things that interact very weakly, like neutrinos, for example, which can go through that shield, or maybe these dark matter particles, which can go through that shield. So if you have a big old shield that stops everything getting inside, apart from things that interact very, very weakly, then maybe when those things get through the shield, they'll interact in your detector now and again, and you can capture.
So wait. Are you saying that the ancient Romans detected dark matter?
They definitely didn't know they were, but they might have been doing something similar. I know you're trying to have me on, but yes. So in these experiments, again, of course, if you are going to wrap this thing in a huge shield to stop things getting in, the last thing you want is the thing that you've wrapped it in is creating particles itself, which are spraying the inside. So you want one of these low background shields. So if we look at a very quick sort of schematic diagram from CDMS, they've got this ancient lead shield, which is round. It's just labeled ancient lead. So they've got this layer of ancient lead, which is around, and then more modern lead. So the ancient lead is actually more valuable, more sought after, blocking any sort of radiation that comes at a lower level from the modern lead. But this is the key sort of inner layer of blocking, if you will. So it was used in this detector that was looking for the interactions of dark matter particles. Also, as you nicely teed up, this Quare experiment, this is cryogenic underground observatory for rare events. So very similar process. In this case, things are actually decaying inside and producing electrons. And what they're looking for was a particular decay of particles called a neutrinoless double beta decay, which is just a particular decay of particles. Now, this is a very, very rare decay, if it happens at all, and it would prove that neutrinos are their own antiparticles, which is important for a number of reasons that we won't necessarily go into. But the point is, this is a very rare decay. So again, if you want to see this happen, you don't want to be bombarded by loads of stuff from the outside, which is going to mimic your signal and create noise and interference and mess. You want to be shielded from all of that that's going on the outside. So what do you do again? Well, you've guessed it. You surround your fancy new modern particle detector with a Roman lead shield on the side.
So you're saying the Romans have also detected neutrinos?
They've also proved the problem of, yes, neutrino mass and all these things that we're worried about now. I'd be careful, because I think some of our ancient aliens proponents probably think they have done that. So we have to be careful when we're saying these things. So the kind of upshot of this is, if you want to look, like I said, at very rare interactions, or you want to measure interactions with rates very, 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 very carefully, you need to be isolated from the outside world. And a great way to do that is with a shield that doesn't produce any radiation of its own. And then we're looking at things like Roman lead or low background steel. Now, in terms of the lead, obviously we know we use lead in nuclear reactors and things, incredibly dense, incredibly heavy. So this is really the best material that you can use, because you get a hell of a lot of blocking potential for your amount of lead. Very heavy, very, very dense. So we're still using these materials over anything else, and this is why it's so sought after. Excuse me. And in terms of the usage, you teed it up very nicely. So in 2010, the Italian National Archaeological Museum gave 120 lead ingots, and as you said, these were had inscriptions from the Roman forges that had molded them, and they came from that Beaufort shipwreck. Now, in terms of preservation, which is something we're going to come on to more, they actually made them cut off the molding stamps from each of these ingots, so that there was some level of record. But I think you mentioned previously, you also want to keep little pieces of these with the shipwreck in a catalogue, so for future techniques that might come along. So they weren't given all of the ingots, and they weren't given 100% of any ingot that they got.
Or at least the ones with the stamps. I couldn't track down about the ones without stamps, but yeah, and I think that's really important, because you never know when some sort of new question or method or analysis might come around. So you want to preserve some portion of everything that you give away. I mean, I think Look, I mean, the media frames this question as archaeologists versus physicists.
Of course, because that gets you the most clicks and
yeah,
most,
that gets you all
excitement,
these clicks and everything.
Yeah.
But of course, it's funny. They interview Elena Perez Alvaro and Fernando Gonzalez Zaba, who's an archaeologist and a physicist who have published on this. And, their article is fantastic. Let me find the name of the article.
I think we have that somewhere.
The role of underwater cultural heritage on dark matter searches.
There we go.
Yeah. So I advise anybody who's interested in this topic to read this, because, I mean, they both agree that the use of these materials in a responsible way for important science, there's nothing wrong with that per se. It's a question of solving this and thinking through, when is it appropriate? What kind of standards do you have in place in terms of documentation and preservation and curation? And how do you sort of negotiate these intricacies in terms of legal, what the legal situation is like? I mean, every single country is going to have different cultural heritage laws, but of course there is a sort of UNESCO framework in place for the protection of underwater cultural heritage.
Now, do you mind if we park that for 2 minutes? Because I want to come on. I want to come on to that next and keep it in a nice clump, because I know you're very, very strong on this. Right. So I want to give you a good lead in and get you going on that, because I just want to clean off what we use for the low background steel. So we already talked about the whole body counting room. So some examples of these being used in the US and the UK. And then I just wanted to flag up before. So steel from the battleship. So suggestions are, although they're not very well documented, steel from the battleship Kronprinz Wilhelm. So this is World War I. So Crown Prince Wilhelm. They believe was used, and from the SMS Markgraf, they believe was also used. Now, there is a little bit of a, what shall we say, urban myth, which hasn't been substantiated, may be true, may not be true, that in addition to these whole body counting rooms that we talked about, some of this metal, this low background steel from these World War I German ships and potentially submarines might have been used in the Explorer probes, and then in the Voyager 1 and Voyager 2 probes, which are now in the outer expanses of our solar system and will soon leave our solar system. Now, NASA has not been able to confirm this. I can't track it down much further than there's a lot of people who say this might be a thing. So I'm not sure if this is... It's one of those things where it kind of makes sense and it could have happened. They knew the steel was here, and then people talked about it, and then A talked about it, and then later B was talking about it after he talked to A. But there's no actual documentation that this stuff was actually used in these. But it would have been appropriate to use it in these ideas. Whether it was, not exactly sure. So in terms of lead, we've got them in these dark matter searches, these neutrino searches. And in terms of the steel, we've got them in these full body counting rooms, and maybe, although it's not been verified, in these outer space probes, which would be really nice, because you're going from a battleship at the bottom of the ocean to, a probe in outer space, which is a really nice through line. But I think it might be more of a really nice editorial through line than it is actually.
It sounds like too good to be true if it's not been confirmed. It's like,
exactly.
Underwater battleships in space.
Exactly. That's what it sounds like to me as well. And I can't find a lot of stuff to verify it. So,
because I also can't see it as something that would be hidden, especially at the time. I mean, would this have been such a thing to have been a scandal type thing? I don't know.
It feels like maybe in terms of America, particularly in the kind of Cold War period, it might have been quite advantageous to say, look, we're repurposing something from, a previous adversary in terms of World War One, and pushing ourselves forward into the modern age with technology that utilizes that history.
I can't see why they'd hide it. In the 50s and 60s, there were not these ethics around cultural heritage. There were no UNESCO conventions, for example. So there's no reason to keep that hidden. It was not breaking any international law or anything like that. It's, and I can't see why. I don't know. It just strikes me as a weird thing. It's just a nice narrative.
So it might just be one of these shaggy dog stories, but yeah, that's something people talk about a lot, but there's not a great deal of evidence to support that. Right. So now that we've cleaned that up, I do want to come on to what you were talking about. So we've obviously talked a lot about the potential, positives of using these materials in terms of science. We talked about how they're used in the ancient world. So there's obviously some really beautiful through lines here from understanding history, and that understanding of history giving science the ability to study the cosmos, deliver more understanding about the world around us, maybe even save lives in terms of medical equipment. However, there are some very serious ethical concerns here as well, which I know you're on top of. So Flint, obviously these materials come from archaeological sites, from ancient sites, whether they be above ground or whether they be under the water. Before we get into the ethical concerns, is there any legal framework to stop people or private entities from going to these archaeological sites and shipwrecks and kind of plundering them for profit, if you will, if that's the right terminology to be used? Is there any sort of framework that stops this? You mentioned the Underwater Cultural Heritage document.
Yeah, that's, I think, the main one. I mean, when it comes to cultural heritage, you have to think about it. You have to understand that this is sort of humanity's heritage. And so there's a large number of international frameworks that most nations have ratified.
Okay. So nations agree to this framework and then they enforce it locally. Is that the kind of idea here?
Yeah, exactly. Okay. Or with international courts sometimes as well. But yeah, most nations have agreed to this, and there's another big one from 1970 that governs the export of archaeological materials. It's sort of why you always need to know. I would never advise anybody to go buy archaeological materials unless like you really understand its provenance and where it's from, because it's probably illegal.
You could be handling stolen goods without knowing it.
Looted stolen goods. And I mean, so it's the same thing for underwater cultural heritage. Of course, you need to have a different framework in place for underwater cultural heritage because those are oftentimes in international waters. So, local laws govern the export of archaeological materials, but how it's conducted is done by the UNESCO heritage laws. But of course, if one country wants to allow the private exploitation of its heritage, like the UK and the US, you can go do metal detecting and whatnot on private land with permission from the landowner in those countries. I actually am fully opposed to that ethically, but it's not illegal. On the other hand, for underwater stuff, it's a different kind of salvage. And so there's this international framework in place that, like I said, most countries are signatory on, but not all. And
you could understand why people would want to go do this salvage, right? So if you look at the numbers, some of the numbers that are involved here. So I think they said it's $33. This is an article from a couple of years ago, so it could be even more now, or it could have changed. $33 per kilogram for these low background lead ingots. These are ones that were salvaged in America from a Spanish galleon, San Ignacio. Whereas it's only less than $2 for your standard lead on the market. So you're talking nearly 20 times the price. So you can understand why people want to kind of go and loot these shipwrecks and these archaeological sites, can't you? It's something that needs to be kind of kept an eye on, because if people are left to their own devices, you can understand why they want to go and loot them.
Yeah, exactly. It's something valuable. And I mean, part of the reason it's valuable is it's difficult to get.
Yeah.
You need to find an underwater shipwreck. You need to find an underwater shipwreck that has a lot of lead.
Yeah.
And then you need to actually go and salvage it. Yeah. And so that's not an easy expedition. And it takes a lot of specialized knowledge to do that, and specialized equipment and whatnot, a huge investment. And at the same time, like I mentioned to you before, this is an extremely finite resource. There's not a lot of this out there. I doubt we've excavated many percentages of what is there to excavate, but at the same time, if we really target this, it will disappear rapidly. And that matters archaeologically, but if you think about it, it also matters for these scientific purposes. If we go use up all this supply right away, then that's the end of us being able to build these facilities. And so we want to be careful about how
or any facility that comes along later where you realize that you need this kind of stuff.
That's my point. And so, we're only going to have this resource available for current levels of technology when we might really want to be thinking about this on an intergenerational level. And that's what these kind of frameworks are in place for, is to, it's there to help with cultural heritage, but that's because cultural heritage is valuable for a wide variety of reasons, which I think in my mind includes uses such as these. And so we need to abide by these so that we actually have this available for future archaeologists and future physicists, right? And that's really important.
In terms of this framework, Flint, does it make a kind of separation between private entities, private individuals, and then people doing things like physics experiments? Because this seems like a little bit of a grey area in the documentation that I saw, where this is kind of for pushing forward knowledge is now kind of allowed. But you could imagine a situation where you had some private individuals salvaging this things, and then it was bought by the scientists to advance knowledge, and then you've kind of got a really grey area there. So how does this framework deal with that use by scientists and potentially the use by private individuals as well?
Well, so that's what the article by Elena Perez Alvaro and Fernando Gonzalez Zalba focused on.
Okay.
And what they brought up was that there is this gray area. So this UNESCO provision, it prohibits commercial usages.
Okay.
So if it's for commercial use, that is strictly prohibited for using
So I can't go
heritage.
dive on a Roman wreck, drag up a load of lead and sell it to the local, hospital or science lab.
Not without figuring out how to get it through legal frameworks.
Right.
And in fact, here's a quote from them, that cryogenic dark matter search. They mentioned that unaware that they were doing anything illegal, the researchers bought the lead. The company, however, got in trouble with French customs for selling archaeological material.
So this was an actual problem during this
Well,
later,
they discovered it later afterwards. And so they discovered that they used illegally sourced lead. And so that was a big problem. While the Cuore in Italy, on the other hand, it was done in collaboration with archaeologists. And that's important. You think about that facility in France, or was that France, the cryogenic dark matter?
The cryogenic dark matter, I think, is over in the US.
In the US, sorry.
Minnesota, and then they had another one somewhere else. I can't remember.
That one in the US, you do realize that those scientists contributed to the plundering of one of these shipwrecks. So that shipwreck I described, in all that detail that we can get out of that Roman shipwreck, we only know that because that was done legally, because the scientists worked with archaeologists.
And they did it responsibly, and they catalogued, and they said what they changed, and and they're still excavating. That's an ongoing project. They're still publishing their findings. There's still new things. I'm looking forward. I saw in a footnote that the zooarchaeologist is studying all the fish remains, and I'm very excited to see what comes out of all those fish remains. And so, there's still, which is a sentence I never thought I'd hear said, but
well, I put my research focuses on ancient animals and how they contribute to the economy. And so it's going to be really interesting.
Cool.
They have 250,000 or 2,500? I forget now. 2,500 jars of that fish stuff, with each of them had several hundred liters in it. And so, it's going to tell us 2,500 amphorae each has 40 liters. But that detail is only available because it was done responsibly. So we do not want to sacrifice that kind of detail for quickly salvaging these shipwrecks. These need to be documented, with rigorous standards. And then we need people to make an informed decision, on when to do this. And this all comes from this article, when to do this, because maybe not every use case actually needs this. Yeah. There can be alternatives, such as like tungsten or different kinds of lead that are more modern.
Or maybe you can do it in software, Flint. So maybe you don't need it's maybe you don't need that shield. That you can in post processing of your data, you can subtract that background away in some way. It's a little bit more work and it's a little bit more difficult, but maybe that use case is easier to do that subtraction than in this use case, where we definitely really need that that lead shield. So you need to be careful. Like you said, this is a finite resource, and if you can get away with not using it, then it's best to not do so.
It's true. And I mean, look, the realities of what archaeology is today is most of it worldwide has been plundered. You know, a lot of it was plundered in antiquity. Thousands of years ago, people plundered tombs like the pyramids. And then, you know, you have today people still doing this kind of salvage stuff or illegal looting. I've had illegal looters come at sites that I work on. The project I worked on in the Crimean Peninsula, you know, I was in charge of the mapping for this excavation, and we set up our mapping software over these datums. And so the datum is just a bit of concrete poured with a nail in it. And some looters came by in the middle of the night, and they thought that that was marking where to dig. So they dug up our datum. They found nothing. There was no archaeology there. It was where we were setting up our equipment.
But people were ready to go on these sites.
And we had to halt excavation and create new datum so that we could do all the mapping and stuff. And I know of other projects where there's been much worse looting, where, you know, a weekend off and they come by and the looters went into their trenches. And so, you know, there's all kinds of, and then when you think about deep water type stuff, it's very common, this kind of salvage, unethical, and most antiquities, most sort of commercial sources for ancient stuff, whether it's metals like this or whether it's, you know, pottery or lithics and stone tools or whatever, it's mostly illegal. And so you should really do your research, because otherwise you're going to be forced to return that. Regardless of you having spent that money, you're the one that needs to do the due diligence.
So while we can gain a lot of knowledge, obviously, with these new particle detectors, we can also lose a lot of knowledge from the ancient world. Yes, that's what I wanted to ask. So we talked about how the Romans made use of the lead. What knowledge, in terms of the work that you do, what would be the obvious types of knowledge that would be left if, say, people were just left to go to the Beaufort wreck and just take whatever they want? What kind of damage would be done to the knowledge base there? What might we lose out about things that we could know about those ancient civilizations?
Yeah, I mean, if you think about it, we lose out the ability to understand ancient trade in the same way. You know, if we just leave the seas open for people to go and plunder this cultural heritage, these shipwrecks, we're not going to have this level of detail ever. You know, we're not going to see that this kind of the large scale shipment of things like lead or fish sauce or wine or anything. We're losing out our entire ability to be able to put together ancient trade. I mean, we actually know quite a bit from ancient Roman shipwrecks. Hundreds of them have been discovered and mapped. Dozens of them have been excavated. Maybe hundreds have been excavated. I don't know. It's a lot of effort to actually do an excavation underwater. But certainly, you know, throughout this entire region, throughout the Mediterranean, thousands of them have been mapped. And so, you know, if we do, and to be honest, a lot of those locations are available publicly, you know, because we publish our data publicly. And so this is a big problem, because if there's a systematic approach to plunder this stuff, it's going to disappear immediately. And like I said, it's not just about archaeology. We're going to lose a big chunk of the archaeological record. And as I hope I made clear, it's an important chunk. It's well preserved. It's a unique snapshot of the past that we can't get elsewhere. And then at the same time, you know, this lead won't exist for future science either. So we won't have it in museums for researchers, and we won't have it for physicists or others or medical inventions and things like that we don't know what's going to come later. We do not want to use up such a rare, finite resource. You know, this is something that we could quickly use up if people really targeted it.
And I'm thinking, just in terms of, you'll obviously know this far better than myself, Flint, but just in terms of thinking naively about the trade, you've then got, you then learn about all the interactions between these different civilizations, the timings that certain things were going on, people's likes and dislikes at certain different periods. Maybe that informs more about the history of what was happening. There's a hell of a lot of information, I'm guessing, that comes out of trade between these different civilizations.
Yeah, of course. No, there's a whole lot. I mean, we get these fun little niches of export markets. Like I have a Twitter thread on how, you know, Athenian pottery, all of the Athenian pottery with graphic sex on it is not found in Athens. It's only found in Etruscan tombs. It's part of a niche pornographic export market. And so, you know, these kind of stories are what makes us understand the past. And so if we all of a sudden lose shipwrecks as a component through which we can understand the past, that's going to make it so we can't put together these narratives of the ancient economy, ancient politics, ancient people as a whole. And some of them are funny little stories, but others, matter. The number of, how we talked about the lead in the Arctic ice cores as a proxy for mining. The number of shipwrecks is a proxy for overseas trade. And so we actually use the number of shipwrecks to understand, ebb and flow of sort of trade as a the globalization of the Mediterranean, or the Romanization of the Mediterranean even. And so, that kind of information, if we start mucking with it and making it not statistically significant, in a biased way, we're just going to plunder the ones with metals. Well, now we've lost, we've created a new bias in our record, if you see what I mean. And we're not going to be able to understand it nearly as well. We're not going to be able to understand the trade in pornography, first of all. And that's a problem.
Very, very, very important. So that raises, obviously, it raises an immediate question is, are there some compromises that we can come to here? So we talked about the use cases potentially on the physics side, where if you don't need it, don't necessarily use it. What is the best practice in terms of the archaeology? So if we're going to continue to remove these objects from the bottom of the ocean, we find a use case where we believe this is the right thing to do. What can we do to minimize the impact on that archaeological knowledge and that archaeological site? Is this about documenting everything that you remove? Is this about having good interaction between the people removing it and the archaeologists, so that they can catalog where things were in relation to each other? We talked about, for example, the ingots that were passed over, not destroying those makers marks and things. What's kind of the best practice if we're going to drag these things off the bottom of the ocean? What do we need to do to make sure we minimize the loss of that archaeological record?
Well, in my mind, everything that's taken out needs to be done by archaeologists who understand how to document. Look, to document a shipwreck since the 1950s, every single layer is mapped in 3 dimensions using photogrammetry or now more recently 3D scanners and things like that.
More physics and archaeologists working hand in hand. This is
the very first underwater archaeologists were the pioneers in doing photogrammetry underwater. They were the pioneers. George Bass, he did that with the Uluburun shipwreck in the 1950s and 60s, and without computers, And so to do this kind of, actually, I guess it was with really early computers. And so, to do that level of documentation is absolutely necessary because of the uniqueness of these finds. So everything needs to be done in coordination with archaeologists. Like I said, I don't think archaeologists have to constantly negotiate between the needs of and between the ethics of preservation and curation and the practicalities of funds. As soon as you excavate a site, whether underwater or not, you're destroying it. Archaeology is destruction. So, the reason,
because the context of where things are in relation to one another tells you that contains information itself, I guess.
That's part of it, the context itself, and we're going to maybe come up with new ways to analyze that in the future. And so, we never want to fully excavate anything. We always leave some for the future for that reason. But 2, also, the archaeology sort of, it gets buried and it reaches a kind of homeostasis where it's preserved for us. And that's why we get these pockets, things like a shipwreck, where we have such amazing preservation of vine shoots, right? But as soon as we lift that
expose it to the air, and now we're on the clock straight away.
We need to figure out how to preserve that, and that costs a lot of money. Right? You have to store metals in a climate-controlled room. You need to preserve the wood from the shipwreck in a waterlogged environment. Same thing with those vine shoots, for example. And so, the funding needs to be there. So if this stuff is necessary, then just like this collaboration here between Quarry and the archaeologists, that involves...
So this is the Boufferet. This is them bringing up the ingots from the Boufferet. Yeah.
And that involved, obviously, funds to not just do the excavation and documentation, but I'm sure for the preservation and curation and display.
So that so when we're considering doing one of these projects, it shouldn't just be, this will cost X for a lead shield. It should be, this will cost X for a lead shield, plus preservation, plus cataloguing, plus the archaeologists who have to go down and do all that.
Which is what it costs. In a sense, you're getting the lead, but you're helping contribute to the archaeological excavation, documentation, study, curation, and long-term curation is the key here. And that's true for any academic archaeological project. We can't just go and dig in these countries unless we provide a plan in place to be able to preserve this heritage that we're uncovering. I cannot participate in a project. I work with projects here in Athens and the Athenian Agora. They can't do that unless they have a plan in place for curation, right? And so that's extremely important, because otherwise it's negligent. Or projects for a long time, they'd uncover a lot of materials and then they'd have no plan in place for curation. And so materials will go to waste. That's why you have storerooms with leaks. Hell, the Parthenon marbles in the British Museum, I just read a report, they're in a room that's still leaking. And so you need to have that stuff, those funds in place. It's unethical if you don't. And so I think that's the key we need to think through. And then, of course, anything that you do contribute for, you're going to melt down this lead after all. You want to be thinking through preserving samples of it, of every single ingot that you give, so it can be analyzed later on if somebody has a new research project or question in mind. And then, I think and then only a sample of it is given anyway, meaning 15%, but of those 15%, you only give 90% of each, right?
And this is something that people are very aware of. So, example from recently, the returning comet sample mission. I forget the name now. It's just on the tip of my tongue. But they brought back this sample from the comet, and what they've done is they've kept most of it for future analysis with techniques that might come along in 10, 15, 20, 30 years. And handed out little packets of it all over the place. But they've kept most of it and most samples from different bits of it in one place for later. So there is a plan in place for kind of long-term use of this thing and understanding.
And I think that's something that people oftentimes don't get. We have these discussions online about
the
Bennu
return mission. That's right, Bennu.
Okay, yeah. But with archaeology, you see people online, they're like, you should go dig that, or you should go do this.
And it's also an asteroid, not a comet. So I've absolutely butchered it. So that's asteroid Bennu return mission. Yes. Sorry.
I'm never trusting you again.
No, I know. I'm done. I'm done here.
No, but people mention things online like with archaeology, you got to go dig this. You got to do this DNA analysis or whatever. Look, I do isotope and DNA analysis. You destroy material. I grind ancient teeth. So I need to have a plan in place that I am leaving material for future people, that I'm only doing a portion of the sample. I'm doing what's necessary to test my hypotheses. And these kind of plans need to be in place, and funding for them needs to be in place before I get permission from like the Greek government to do my analyses, right? And so it's the same thing with everything. We need to have long-term plans in place, because this is important, valuable heritage material, whether it's a sample of an asteroid, which is going to be very rare, or whether it's lead from an underwater archaeological site or sheep teeth that I'm testing, It's all valuable in its own right and quite rare and needs to be preserved.
Have there been any particularly egregious examples, Flint, that you're aware of? I'm sure you are aware of some, or notable examples of, individuals or companies plundering archaeological sites for profit, or even under the kind of guise of doing good. So, I mean, I can think in this country, we have people still, even last year, nicking lead off of church roofs to, God knows, I don't know if they're selling them to Geiger counter people or particle physics experiments. I don't know. They probably just want the metal and they're selling it as normal metal, right? In terms of these underwater sites, a lot of them are now kind of mass graves, particularly if you think about the ones that are not particularly old. We're thinking back to World War I, World War II. These have body parts and whole corpses still kind of floating around in there potentially. So these are essentially, mass graves, unmarked mass graves with unburied people inside them. These are temples or places of worships that are being plundered. Are there any other kind of egregious examples of where people have destroyed archaeological sites for?
I mean, look, unfortunately, archaeological sites are destroyed all over the world. Sometimes for very practical reasons, you need to build a new building. And of course, there's rules in place, but, a lot of times developers don't follow the rules in lots of countries. And then, of course, you have examples of things like looting, funding terrorism. ISIS would do mass looting of archaeological sites in Syria and elsewhere. And so, there's a major industry
Yeah.
for looting on land and underwater archaeological sites that, I mean, this is why I want to bring this up is because it is an egregious problem. And to be honest, I'm very, very opposed even to just sort of offhand private collecting, going out and doing metal detecting or going and walking the landscape to pick up arrowheads or something like that. You get enough people doing that, and eventually you're systematically destroying an archaeological landscape. And that's the problem is you get enough people doing it. It starts off as a fun little hobby 40, 50 years ago that a few people are doing. But these days, so many hundreds and thousands of people are doing it on such a regular basis that it really does contribute to just the egregious destruction of archaeological landscapes. And so sometimes it's legal, sometimes it's semi-legal or quasi-legal, and then because, some of these metal detecting finds, people are ethical and report them. Others of them, they don't, though, right? We know that. Well, archaeologists pay attention to this. Paul Barford has a blog that sort of documents this, and he's shown repeatedly that only a small percentage are actually reported by these metal detectors. And then, of course, there's the very illegal type stuff like that funds terrorism or drug cartels. The archaeologists I know that work with sort of the U.S. Department of State, for example, they describe how, they have to teach customs officers not just to look for drugs, but to look for antiquities, because oftentimes the antiquities are actually the more valuable part of the smuggling business and not the drugs. And so, it's something that you need to look for because there's a lot of money that goes into this sort of dark economy, and it's a real problem. Yeah.
Yeah. Makes sense. So as we sort of come to the end of this, I guess, do you want to kind of wrap up your sense? So obviously, as a particle physicist, I want to see these experiments go ahead. I think they're very, very useful. They set limits on various things. They find various things. What is your overall feeling on whether we should go ahead with using, these materials from the ancient world for science experiments, for things going forward? Is it getting that balance right between the positives that we can get out of it and the negative destruction of those archaeological sites? Is that the kind of key watchword, the balance, or the cost benefit analysis?
I think developing clear standards is important. I mean, I really do agree with Elena Perez Alvaro, the archaeologist that published with the physicist Fernando Gonzalez Zaba. And I think that they ended it by saying, even if the dilemma could be resolved by adopting a case-by-case evaluation, there is a risk of a growth on the use of ancient lead for other kinds of experiments motivated by market expectations and not by knowledge. And so its use should be regulated. So the extraction and documentation is done under archaeological standards. And I mean, I fully agree. I think physics research needs to go ahead. I am all for, in the correct way, using archaeological materials, but it needs to be done with legal frameworks in place, with ethical frameworks in place, and with sort of physicists, whether it's international or national sort of legal experts, and with archaeologists sort of all together figuring out standards and ways to make this work. I certainly can see a use for it, but it does need to be done very carefully, and it certainly should not be done left to sort of commercial actors. I think that would breed sort of illegal activity and not thinking through all the issues here. I mean, I've learned a lot from talking to you about this and researching this, and I hope you've learned some, and people paying attention. And it takes that kind of expertise and background of knowledge to sort of to come together with these sort of different perspectives.
And we physicists are sometimes bad at this, Flint. We kind of, a lot of us think we know everything, and we can just kind of wander into other fields, and we're so amazing because physics is so difficult. And that's not the way to go with this. There's a hell of a lot of knowledge that you can be trampling on things that you don't even realize that you're trampling on by, I need this lead shield. This is amazing. I'm going to discover something new without even realizing the knowledge that you could be destroying along the way. So as you said, it's very important to get those multi-skilled teams together beforehand.
Yeah. And I mean, look, part of what the advantage of an archaeological perspective, now I'm going to say we got the right perspective,
as long as we're all in the room fighting, then that's okay, because we end up somewhere in the middle. So that's good.
This is for the physicists, though, so an archaeological perspective oftentimes is long term. We look at the deep human past over the long term. And I think that's key, because if you want that lead shield, that means a physicist in the future is not going to have a lead shield. And so that's something that we all need to keep in mind as well, right? A long-term perspective is really important and valuable.
And that's very difficult sometimes when you really want to get on with your experiment or something.
It's
very, very important.
But it's important. It's important, especially when you think about all the changes that we've wrought on the world from nuclear experiments or silver mining. Yep. We can see what we do to the world, how humans alter the world. And we all see that. Physicists see that. Archaeologists see that. Yep. And so I think it's something we can come together and think on, though, if cooler heads can prevail.
I think that's a really important message. And I think that's a really, really good place to leave it. Flint, thank you so much for taking the time today. I know you did a hell of a lot of research as well. I learned so much about this topic, both in terms of the archaeology and the science, just by researching beforehand and then talking to you now. It's been absolutely fascinating, absolutely amazing. I've really enjoyed it. It's been fun as well. And I hope everyone out there has enjoyed it as well. I've got, in this kind of wrap-up section, I've just got a section for any other business. If there's anything else you wanted to bring up to people, or anything else you think might be worth saying. I know you might be going on a certain podcast soon, if maybe you wanted to advertise that. I don't know if that's something that's out there to be said.
So I will be sitting down to talk with Graham Hancock on the Joe Rogan Experience in April, I guess.
Okay.
To sort of explain why there's no evidence for not just that there's no evidence. Look, one of my key arguments here is
this is for ancient apocalypse, right?
Ancient apocalypse. So there's this idea that there's a lost Atlantis, an advanced Ice Age civilization, and most scholars sort of approach this saying, well, extraordinary claims require extraordinary evidence, and there's no evidence. And I agree with that. There is no evidence.
There are a lot of clicks, though.
But you know what? I'm going to take a different tack. My goal is to show that we actually have a lot of evidence, and it disproves this. Okay. There's no chance ever that there was an advanced Ice Age civilization. There's a reason why archaeologists aren't searching for it. So, tune into that, but also check me out on my YouTube. Yep. I've started to do some interviews with archaeologists that are affiliated with projects that are brought up on ancient apocalypse and stuff like that. So check me out on YouTube, Archaeology with Flint Dibble. And I'll have you on and we'll discuss dating and stuff of the pyramids at some point.
Yeah, we definitely should. So there's a hell of a lot of other crossovers for archaeology. We talked a little bit about dating techniques. Luminescence dating was something that I hadn't come across. Really, really fascinating. I talked to a gentleman who did some of the dating of the skeletons in Sterkfontein, had some other radiometric dating that was very, very interesting. Muons, as you kind of alluded to there, have been used to map sections inside the Great Pyramid of Giza. So lots and lots of fantastic crossovers between particle physics and archaeology. And yes, please do go. I will make sure all of Flint's socials and his link to his work are down in the description. His archaeology channel is awesome. Penis bones, if you're interested in those.
Yes, that's my favorite video. The top 6.
Do you want to tell us a little bit about that?
Yeah, because I study ancient animals, right? And you know that some animals have penis bones. So carnivores have penis bones. Pre-humans have penis bones. A lot of primates have penis bones. But
why do we care about penis bones, Flint?
Apart
from the obvious hilarity of said things.
Because they tell us about the past, so we can actually use penis bones to help understand the domestication of the dog. Some penis bones were turned into tools. So, for example, raccoon penis bones were turned into fishhooks because they're shaped like a fishhook. Penis bones are actually...
sorry for the female raccoons, but okay.
Well, I show pictures of a lot of penis bones, and I have to say the penis bone is cool because it is perhaps the most diverse animal bone in all animals. It comes in so many shapes and sizes, and they're really weird and they're really cool. There's some fun stories that I pulled out, some 6 fun stories of ancient penis bones. Yeah.
Right, go ahead and check that out immediately. I will, as I say, make sure all of these links are down below. Flint, I would like to thank you again. This has been absolutely phenomenal.
Yeah.
I've really enjoyed it. I'm sure everyone else will too. And next time something comes up, or if we want to cover those other topics, let's get back together and we'll have another chat, buddy.
Let's do it. Thank you so much,
Awesome.
Sam.
Thanks, buddy. Take
Ciao.
care. Bye now. Bye. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.